Internet of Things, what is it? It is the idea that we can integrate communication and computation with all kinds of everyday devices and objects. So here is just a set of IoT devices you can buy today, from the Nest thermostat to smart picture frames, smart refrigerators, smart light bulbs, smart insoles, smart cars, smart fitness monitors. My favorite is this one on the bottom right. It's a smart shirt you wear, and it monitors all your health signs as you're exercising. The reason I like it so much is I asked them, hey, how do you do the power bus? I remember reading about this a while ago, talking to somebody who said it's really hard. The shirt goes into the laundry and it just wrecks all of your connections. And they said, oh, we can't tell you it's patented. To which I said, wait, a patent is public, right? Anyways, so just trying to hide their secret sauce, and I can just buy a shirt and cut it open. But so the Internet of Things can be used for all kinds of stuff. And when SDSI was first starting, that is when we had this first set of seminars of people broadly across the university talking about data science problems and challenges and techniques, there's one person in particular whose presentation really resonated with me, Noah Diffenbaugh from Earth Sciences, who's very, very concerned about global warming and climate change. And his questions related to how can we use data science to better understand ways that we can reduce our effect on the environment. And so this is just an example of global warming, where, gosh, this used to be a place that was covered with glaciers and snow and is no longer. And so we joined forces, basically trying to ask this question of, could we use data science, the Internet of Things, to say something about, in particular, California's drought. And so here's a paper by Noah's group, basically talking about how global warming and this climate change has affected drought risk in California, looking at soil moisture levels, and this is something we're all dealing with today with low water levels. And basically, the results of his work show that, gosh, there's really high confidence that it is us who are in fact making the world warmer, and this has tremendous impacts now for, you think, California's agriculture, among other things. And so the question we start asking is, what could data science do? What is something we could do at Stanford to try and help with this problem? And so it turns out, if you go to Stanford, Stanford consumes a lot of water, but there's this really big problem, which if we just look at the small microcosm of Stanford University, we don't really know where a lot of the water goes. So as an example, this is the monthly bill that Gates Hall, the computer science building, receives. And all it kind of tells them is, look, you spend $340 a month, that's your charge on water. This is how many gallons of water you're consuming per month. There's no idea as to how much of that is during the day versus at night, who's using what. Is it that there's a leaky faucet somewhere? We have no idea. We have no visibility into where water is going. I just used this report from Gates Hall because it's the one that I have, but the same is true of dormitories and residences. We have no idea where the water is going. We know a lot is going to the golf course, right? But within a building, right, I have no idea who's using what. And the high-level point here is, for these kinds of resources, whether it's electricity or whether it's water, we have lots of aggregate high-level data. We know this building uses more than that building. We know we use more in the winter than in the summer. But we have almost no information on what individuals do. And ultimately, if we're going to change our usage, we need to change the behavior patterns of individuals. So simple questions such as, is it that for all the students in this dormitory, they're sort of all their water uses within about 10% of each other, at which point you might decide, gosh, what we need is across-the-board reductions through a bunch of measures. Or it might be that there's one or two students who use 5 times as much water as the average. And really what you want to do is do an intervention with them and get them to stop leaving the shower on all day long. And so the question is, could we build some kind of an IoT system which would let us collect this data, allow us to understand where water is being used at Stanford, but also, and this is kind of the tricky and interesting part, is can we do it in a way where we maintain user privacy? And this is the secure analytics for the Internet of Things. So for example, could we collect all this data on these students and give them recommendations of what they could do without actually knowing who the students are or who's actually using what? That is, do this in a way such that the thing that is generating messages, generating all of this aggregate knowledge, doesn't actually know who's doing what, such that if someone compromises their server, the IRB is not upset at us. And so at a high level, what this means is what we need to do is we need fine-grained water usage data on the level of an individual. right? This means like at a per fixture precision, we want to know like this faucet is using this much. We want to somehow be able to tie that use of that water at that fixture to a particular person. For example, it could be some showers are used for long showers, others are for short showers. Is it that if you raise the temperature in the bathroom, people take shorter showers? It turns out there's this one dorm at Stanford, built in the 60s, terrible ventilation, and so it gets really steamy. So what the students do in the winter is they open up all the windows. And so now the bathroom is really cold, and there's a hypothesis, one of Noah's hypotheses is that, gosh, you open all the windows, the bathroom is cold, people take long, hot showers. He says this is what his son does, and so this is hypothesis. So now if we perhaps actually raise the temperature in the bathroom, would we see less water use? So what we want from an IoT standpoint is we want a wirelessly networked device which is going to allow us to measure the water flow and the temperature at each fixture at second granularity for 24/7. Whenever there's water flowing, we want to measure this data. And also collect data on who is using that fixture. And this is where it starts to get a little interesting. And so what we did is we sat down and thought through what are the requirements we need for this device, because there's no device that can really do this today in a cost-effective manner. So we need to collect accurate water flow temperature data while it's in use. It has to be self-powered. We don't want to be replacing batteries in the bathrooms every couple of weeks. It has to be reprogrammable so that we can actually, if we decide we're going to do some in-situ data analysis, we can then reprogram the device to do so. We want it to communicate wirelessly with mobile phones so we can upload data to the cloud automatically, as well as also figure out by phones and other Bluetooth devices who is close to the fixture. It needs to operate at high temperatures, 135 degrees Fahrenheit. You sort of put as the high end as to what the water temperature might be. And because people are showering and using the sink and perhaps drinking water, it has to use human-safe materials. So we prototyped this device. Here's the sensing device as a nice a CAD diagram. And so inside that top part, there's a turbine, which is as the water flows, it gathers power, and so it charges a battery, so water flows in. Also, as this thing spins, you can measure the ticks and figure out what the flow rate is. You put a thermistor in there, and you can measure the temperature. So here's the basic hardware details. We're using an off-the-shelf system on a chip, the NRF51822, uses Bluetooth Low Energy, and there's a Cortex M0 processor there, and you can see the energy harvester, the little turbine down there. And so we built this whole thing, custom hardware, software, the enclosure, lots of fun. Students had lots of fun. Developed gateway software so that we can now take this data off these devices. There's something running on your phone, data goes to the phone, it gets sent to the cloud. And there's a bunch of communication protocols to make sure we get the right data. We don't lose something if somebody uploads the data, then deletes the app. Now the part where this starts to get interesting is now we've sent all this data up into the cloud, and all this stuff has been encrypted so that if somebody tries to crack into it, they can't get usage information. But now what we want to do is we're getting all these streams of data about what fixtures are being used and what device around it. Questions we want to be able to answer are, can we actually start figuring out who used this shower, who used this fixture, just based on this really noisy data of proximity? Furthermore, are there ways we can start to ask these questions without violating privacy? So we can say something about, say, the distribution of water use across a dormitory without knowing who's in the 95th percentile. But the really key thing here, and this is the reason why I've gone through this effort of building this device and doing the software and the hardware, is it's really critical to do this with real data from a working system. So in the past 15 years, we've played tons of IoT-style systems, and what you find is inevitably the real world never matches the lab. You have lots of great ideas, but when rubber hits the road, it can be the data that comes in is completely different. So you want to test and deploy in a real system. And so that's what we're doing. So it turned out that the hardest part in this so far has been the enclosure. So I listed all of these different things which the system needs, and it turns out the combination of them become really tricky. So we thought, gosh, we'll just 3D print these enclosures. And we've got these 5 requirements: human-safe materials, 135 degrees Fahrenheit, waterproof, reprogrammable, allow wireless transmission. Turns out if you combine all these things, the set of things you can actually do is pretty narrow. Wireless transmission means you can't use metal. Reprogrammable means you can't just coat it in resin to make it waterproof. That's what a lot of products do. The combination of human-safe and 135 degrees Fahrenheit, turns out there's actually no 3D printed material besides really, really crazy stuff that SpaceX has and we don't, that meets those requirements. So we zeroed in after many, many iterations. Here's just, I think, 4 of the 23 different versions of the enclosure we built. First step is to printed a material that is temperature safe, so it has a high heat retention factor, this high temperature ABS material, then to coat it in 6 micrometers of parylene, which is medical grade safe, such that we're not introducing all kinds of bad toxic things into people's water. We have gaskets to seal the turbine compartment. You can see the gasket there on the bottom. It's great. And so this is the plan. We've got the enclosure. It's working, hardware, software, everyth's great. We'll deploy it in the autumn, in time for the school year to measure. So we deployed it in our postdoc apartment. The postdoc's been leading the project, Larinas. And yeah, it works great. It's awesome. So here is a graph of the measurements he took on the flow rate, gallons per minute. About 1 gallon per minute is a nice low flow shower head. Turns out Stanford is thinking about installing even lower flow shower heads to punish students, down at 0.6 gallons per minute. And even down at 0.6 gallons per minute, we can easily sort of gather enough power from the turbine such that a 5-minute shower a day will keep the device powered indefinitely. So students did a great job. It's totally awesome. We have a perpetually powered device if you just take 1 5-minute shower a day. So everything's working well. We're now going to deploy at Stanford. It's awesome. So what happened? So this is an exploding water main. You see water just shooting in the air. And so what happened was, it turns out that Stanford has astoundingly high water pressure. I was talking with Kunle about this. You have to put flow restrictors for your sprinkler system so your sprinklers don't explode. And so, in fact, all of these enclosures started literally exploding from Stanford's water pressure. So, oh gosh, so we thought we were going to deploy in the fall, so you have to go back to the drawing board, redesign, all these kinds of things. So here's some examples of, there's a crack, I think you can barely see it on the nozzle there, caused by the high water pressure as you turn the shower on and off. So we strengthened the structure so we won't have cracks. Well, it turns out that the water pressure was so great that the turbine, where it was resting there in the center, was causing the plastic to bend and bulge until finally that would crack and then water would pour through and short circuit all the electronics, and also you no longer have a good rotation, so you can see there's a bulging there. Also here it's bulging up from the other side, so the water pressure is just distorting the entire enclosure. Okay, so we made that a bit stronger, right? But then it turns out that just the pressure from the water, that 6 micrometer coating to make it safe, well, this thing is just grinding that coating off. So many, many steps later, and many more iterations later, this is the cost of the enclosures of all of these new things because of all of the things of Stanford's water pressure. So where are we today? The short answer is that we've moved just now from a 3D printed enclosure to an injection molded, which solves all these problems. The basic issue is you have a big upfront cost and a small per unit cost, so maybe we can produce many more than the 200 originally intended. That's the goal. And so we're going to have the first one back in about 2 weeks, and our hope then is to actually start collecting the real data to start doing this analytics on IoT data. So that's the current status of this project. Our goal at the high level is to do secure analytics on IoT data, so we're trying to collect some IoT data. Unfortunately, the water use at Stanford, gosh, the water pressure has been a bit of a wrinkle. On the other hand, I think this is actually a great example of, this is sort of the difference between taking some assumptions to what the data would be like versus deploying a real system. There's always a few hiccups at the beginning, but then once you do, these are going to be real data sets that are invaluable. We'll be able to deploy this at a pretty large scale. Our hope is to make this an instructable, have anyone who wants to be able to deploy this system and start collecting data. And so we're going to deploy these over the winter holidays so we can start collecting data in the winter quarter. All right, so any questions? I'm also happy to answer questions about the Internet of Things. So, yeah.
So talk about the installation costs, and where did you install this thing? Is it under the sink, or in the wall, or is it between the downstream of the nozzle?
Yeah, so in our first deployments we do in the dorm, it's going to be the fixture point from the wall, right? So like at the shower head or down underneath the sink where the hot and cold come in.
So when the shower is off, there's no pressure inside the device.
That is correct. Yes.
It's a good thing.
Yeah.
Could you say a little bit about the emerging protocols? Will they be by field, or is there anything in common for secure Internet of Things?
Yeah, so that's a great question. So I think there's a real debate right now as to what communication is going to look like. In particular, are we going to have a model where these IoT devices directly talk IPv6 or IP? They're internet connected, you can ping them, they can ping things, right? They're little internet devices. Or is it going to be that they're mitigated and mediated by a gateway? So I talk Bluetooth Low Energy to a gateway, then software on the gateway talks the internet. But the thing on the edge is not an internet device. And I think that's going to actually greatly determine what kinds of protocols people use, whether or not you're going to use the standard protocols like transport layer security or IPsec, or whether you do something special on top, whether like you just encrypt your data then use your own custom protocol. So I think what's interesting is if you look in the past 2 years, IoT people have been talking about it for a decade. But what really took off were two things. Number one was just a set of microcontrollers that suddenly became available at great low power. Cortex-Ms, they're low power, just suddenly became really stellar. The other really was Apple when it introduced iBeacon. So underneath, iBeacon uses Bluetooth Low Energy. That's been around since 2006. First it was Wibri, et cetera. But what happened was all the chips and all the phones in theory supported it, but nobody had software support. And so suddenly Apple said, we're going to have this thing iBeacon, and suddenly we have these devices that talk Bluetooth Low Energy, iOS supports it, now suddenly Android supports it. And so it was this merging of the embedded space and ubiquitous computing with mobile computing in your phones, right? Zigbee, BLE has sold more units in the past 2 years than Zigbee did in 15 years, because nobody wanted Zigbee to be running on their phone. Nobody wanted to pay. And so I think that's what's governing the communication protocols, is those two changes.
I have one question of my own. I didn't quite understand how you're going to detect the user of the water. Presumably, you're not going to have a camera in this device.
Great. So this is exactly the question that I'm going to ask Yuri, right? You notice he's at the beginning, right? And so the point is, what data do we have? We're going to have particular water uses, that is durations and temperature, right? Or particular patterns. Like for a shower, it's going to be mostly durations and temperature and time of day. For fixtures, you might actually have particular usage patterns, like in the sense of I turn the faucet on or turn it off, right? And then we're going to have very rough proximity of BLE devices. So if you're carrying your phone, right, or if you have a fitness tracker or something like that. And so the question is, you're shaking your head.
Am I in the shower?
I don't know, right, so that's right. So the part of the points here is that, I didn't talk about this for the gateway application, it's an opt-in system, right? And there's no question not everybody's going to do this. It's going to be very, very coarse data. But this is exactly the question of how can we, based on the data that we have, start to figure this out? Until we see the data, we're not sure. So that's the question we want to answer.
Temperature, because people, I guess, use different temperatures for showering, and maybe that could, at least you can sort
Absolutely, yes. So you have temperature, time of day, duration of use. Like, can you actually start to assemble some kind of signatures of use? Like the athlete who always comes back from practice at 4 o'clock, right? Versus the person who gets up for their 9 a.m. class. So,
interesting. Yes?
Or a weight sensor on the floor.
Yes, I don't think, so that sounds like step 2, like let's pull up the tile and put in a weight sensor. Maybe that's step 2. So.
Or you could have like the Xbox, what is that device that they have?
The Kinect, yeah.
The Kinect,
I don't think people want Kinects in the shower actor. Right? Yeah.
It's not taking pictures, it's just...
Right, so again, and don't forget, it's also, the one question is, gosh, do we have to really pinpoint this data is associated with this person? Or can we just say, look, we know that these two people, they're taking showers in different parts, there's 2 showers going on at the same time. Can we then disambiguate that? And it all gets this trade-off of privacy versus the analytics that we can do. That's something which, actually, I'm most interested about this is, the current model is always you just collect all of the most identifying information you can, everything you want, you dump it in the cloud, and then, gosh, everybody's private life is open to compromise. So how can we limit as much as possible, either through cryptographic techniques or just by limiting your data acquisition, yet still reach reasonable conclusions?
It is true that you don't like low-hanging fruit. I would have started with a one-family home where the water, the pressure is lower, and there's only 3 or 4 people that are using the water. And
I really
you have to start with a dorm and lots of people.
It seemed great. It was deployed in the dorm, and then, so.
Phil, I have a question.
it seems to me like we're in this funny state with Internet of Things. It's like, it reminds me of like 1994, 95, when the first internet came around, and it wasn't really.
It's gotta be big.
Yeah, and people were saying it's got to be big, and other people were saying it's a fad, you know. And it seems like we're searching for that killer app, and there's all these things that don't seem quite right. Do you have a sense we're getting any closer to like the Yahoo of the Internet of Things, or something like this, whatever, Mosaic, whatever it was that came out back then?
Yeah, well, so, I mean, what is the killer app of, you know, the internet, right? And what was the initial killer app? And advertising, right, and sale, right? And now it's social media, all that kind of stuff. This is something which has, I think, the field has asked itself for the past decade. And the general answer seems to be, like, look, there will not be a single killer app. I mean, one you could look at today are all of these home safety security systems, like whether it's your Nest Protect or your cameras or all that kind of stuff which people are using to better understand their home. The other is all these fitness trackers, right? People want to be healthier and safer. But I think the answer is there's going to be many, many applications which sort of populate this space. But I think the analogy is absolutely right. It is like 1995, right? We know it's going to be big, but we don't really know where it's going to go yet. And from my perspective, one of the big points there is I would like to not repeat all of the security nightmares that the web has brought us. Like, we know if we just turn the crank, it's going to be a disaster. And this is the whole Secure Internet of Things project. Like, can we just, from first principles in the beginning, think about this a bit and do it better such that we don't have all of the tremendous kinds of security flaws?
Just giving Phil ideas. Advertising is the future, so this shower device will start telling you, you should use Head and Shoulders shampoo today.
Oh, boy. Oh, boy.
Or just tell Amazon and they'll ship it to you.
Yeah. I want to save the planet, man. Against, no low-hanging fruit. So.
That last question or comment of yours is a great segue into a discussion maybe about where you are with the programming frameworks for IoT. I know that's a big part of the emphasis in your group.
Yeah. I mean, so this is one of the applications that we're implementing in the programming framework. But what Chris is commenting on is, gosh, I've just talked about little hardware designs, what's the analytics, but gosh, how are you going to program this? It's these applications that are embedded devices and mobile gateways in the cloud. What's the programming framework you use? Today, what really led to Web 2.0 is the introduction of frameworks like Rails and Django and PHP once it took on Model 3 Controller. If we had those frameworks now, we would do much, much better, right? So you have the ability to prevent common bugs and also just make development faster. And so we're actually developing a programming framework which will, the hope is, right, and the goal is that you'll be able to describe your application and it will do things like automatically encrypt data for you. If all you need to do is test identity, then you can encrypt it. All you need is, some identity preserving encryption, and the data won't actually be known. So even if your servers are compromised, you haven't leaked anything. And given the recent trends you're seeing, like with Apple and with Google, about wanting to not be liable for when people break into your devices, whether it's people with ill intent or the federal government, we think this is actually pretty promising. So.
Well, I have, Jeff, yes. And then I'll ask one question myself.
Let's see. I live on Stanford campus, and we have this radiant heating system. And I know when they replaced the pump, they sold me a pressure reducer. And I'm thinking, about 55 years ago, I took a course in fluid mechanics, and I still can't figure out how it works, because what we were taught was basically you can't do that. So I'm wondering, I don't know, maybe they just billed me for something and it doesn't even exist. But if it does exist, why aren't you using that to protect your devices?
Great question. So gosh, why don't we just do, the flow restrictor, right? Which is actually what some of the shower heads have integrated. So it turns out, in terms of the physical form factor, it doesn't fit. Like, we can't. So you start getting the situation, you have the enclosure, and then there's this flow restrictor in front of it, and suddenly the person is no longer standing inside the shower. Instead, they're standing outside the shower. If we could open up the wall, we totally would install it, right? Yeah, that's the first question. Why don't we just do that? And we talked with Stanford and the people, and you can't. We're trying to do something that's small, so people are still standing inside the shower. So you can also ask, like, why not just integrate that into the enclosure, right, or some structure like that. So.
So I have a question. You're the co-director of the Internet of Things program. So maybe you want to comment a little bit on what that program is and how it relates to SDSI?
Sure. So, I mean, as I think first of all, there's significant overlap, as I think, on the data science side of things. We very much want to start having these IoT applications where we're collecting real-world noisy data so we can start doing data science on it. Hence, Chris Ray and Yuri are involved in this project. So there's that overlap of secure analytics on the Internet of Things. That's the overlap. The part of the Secure Things project that doesn't overlap with SDSI, sort of this separate part of it, is like, developing secure operating systems, network protocols. All the things are going to sit beneath the data science, these systems and electronics. One of the questions we're asking is, you deploy one of these IoT systems, you're going to deploy it for 20 years. If you wind back, what was computer security like 20 years ago? Think Windows 95, right? So what does it mean to deploy a system today that will be still safe 20 years from now? How would you design something like that? And I think one of the points that comes out of this, if you want to be very science fiction-y, in 20 years, quantum computers might be real. Like, we might have quantum attacks against crypto systems. So we need to actually be able to support cryptographic mechanisms and security that are resistant to quantum attacks. What does that look like? What does that look like on your circuits in your system? So I think those are some of the questions that we're asking in the Secure Internet of Things project. Very much like, how is all this data going to be generated, low power and operating systems, such that then we can do interesting data science.